Hello, in this video we're going to learn about the inverse norm. So in our last video we learned about the normal CDF where we could use the button on the calculator to find the area inside the curve if we were given a certain cutoff or two cutoffs along the curve. So there's actually a button in the calculator that goes the other way. If you knew the amount of area inside of the curve, you can push this button to find what value would have cut off that area. Now, just like the CDF, we do have to kind of be careful because the calculator is limited in the way that it can find it. So we'll have to do some tricks, but remember that it's still a lot better than having the old way back in the day with these charts, because then they would have had to look through all of these numbers, find the one that it was closest to, which usually was two of them, and then go and find those numbers and kind of average them and try to feel it out. And of course, that was not as exact. Now, a slight disadvantage to doing it this way, even though it's so much easier for us, and it's actually more accurate because we have, of course, technology doing these things for us instead of our human rounding, is that the XYZ program sometimes came in from using the charts. And so sometimes it'll be off by like 1,000th of a point. So if you're working on a homework problem and you see that you've gotten it wrong just by that 1,000th of a point, just regenerate the problem and try it again. It was just that specific example. It was a little bit further off than they usually are. So try not to be frustrated by it. You were doing it correctly. And if you're ever unsure, of course, you can always contact me. So the calculator always finds the area to the left, which is actually what the charts did back in the day as well. So they found the area over here to the left of a certain cutoff score Z. So because of that, the calculator programmers kind of did that same thing. So we have to kind of trick it if we want to do anything other than to the left. We'd have to find to the right or maybe a between, or occasionally we find the area in the two wings, like we've said before. So they had to do all these tricks with the charts as well, but then it was even more complicated. So all we have to do is say, okay, if I knew the area in the left was such and such, then remember that the whole area under the curve was equal to 1. So if I needed the area to the right, I would just have to take 1 minus the value to the left. So in our calculator, we can always put into the left, just easy. If it was to the right, we would just do 1 minus the number that they give us. And then we have some tricks for the between. So the trick for between is a little bit complicated, but of course you're allowed to have the note card on the test, so you can jot this down. And if you stop and think about it, it makes sense too. So this diagram here kind of shows us. So the wings, if we knew what was in a symmetrical wing, we'd say, okay, well, this much area was in 2 wings and the calculator can only find left, then I would just have to cut it in half because half of the area would be in this wing and half of the area would be in this wing. That example doesn't really come up very often, but I like to show that because it helps us understand the next one. So if I needed between, so for example, right here, the green area, they were giving us this number. And of course, we're going to see examples. And I want to find these 2 arrows right here, these cutoffs that cut off this specific area. Then just like I was saying, the purple is double. We can kind of use that idea. So we say, okay, I know that the whole area under the curve is equal to 1. I've been given the number here in green. So if I did 1 minus that, that would give me the area in the 2 purple wings because I know that the total area under the curve equals 1. So by doing 1 minus the number, I now have the area in the 2 purple wings. Now, just like I was saying here, if I knew the 2 purple wings, but the calculator can only find the cutoff to the left, I could just cut that new number in half. So I know that's kind of confusing right now, so let's go look at some examples. All right, so in this first one, we have the area to the left. This is the easiest one because that's what the calculator automatically does. Now, in the same area that we did our normal CDF, we have an inverse norm. So we're going to go second vars, just like we did before. So second and then the vars. And then instead of going to that second option of the normal CDF, get it to show you there. The third option is the inverse norm. So scroll down to the third option, which is INVNORM. And then depending on your calculator, if you do have an older calculator, it'll just have it on the blank screen for you to type in. If you do have one of the newer ones, it should give you this right here. So there we go. Let me see if I can get it to focus. So it asks for the area and then the mean and the standard deviation. So we're going to input these three values. And of course, you can see it on your calculator. So in this example, it says that the area to the left is 0.15. So in the top value there, we enter the 0.15. You can enter it as 0.15 or 0.15, either one. The next one, the mean, if it's the standard normal, those are just always the 0 mean and 1 standard deviation. So if it's anything different where they give you a story with context, we'll use different numbers. But if it's something like this where they assume it's the standard generic normal bell curve, we use 0 for the mean and 1 for the standard deviation. So in my top value, I've entered 0.15. For the mean, I entered 0. For the standard deviation, I entered 1. And then the next line there says paste, which just puts it back onto the home screen for you. This is what it would have looked like if you didn't have that newer, fancier calculator, where you would input the three values with the commas, and then you hit enter to get the value negative 1.036. So I would type it in the calculator. It should look like this on your calculator screen. And then after you hit enter, it should give you this number right here. And I always like to go out 4 decimal places. This is kind of standard rounding for these types of problems. And the reason is because remember back in our charts, we had 4 decimal places. So we're just kind of paying tribute to the charts we used to have. So that would be the answer for this one. So that means on the bell curve right here, the value negative 1.0364 would cut off an area of 15% over here to the left. So if I drew it out like this, 15% would lie right here, whereas for of negative 1.036 cuts it off. And this makes sense because I did expect 15%, which is less than 50%, to lie to the left of the mean, which was, remember, always 0. So 0 is here in the middle. We are to the left of the middle, which makes us have a negative answer. So it all goes together. Okay, so this one, it says the area to the right. So that means we're going to have to use one of our tricks. So remember that the calculator only knows how to find the area to the left. So we just have to trick it a little bit. And if I knew that 8% was over here to the right, then 1 minus 8%, or the other 92%, would be here to the left. So I say, okay, calculator that only knows to the left, let's just tell it the 92. Now, you could type in 92, or you can actually, if it's something that you couldn't just do in your head, you can actually type it in exactly like this, 1 minus 0.08. And it can do the calculation for you right there on that screen. So when you went to your inverse norm and you had that blank screen there, you would actually just type in the values 1 minus 0.08, and it would calculate the 0.92 for you. Okay, just like before, we would have the mean of 0 and the standard deviation of 1. And then that's going to give us our answer of 1.4051. We round this. Careful of your rounding. 1.4051. Okay, again, this makes sense. I expected this value right here to be to the right of the center. So a positive answer makes sense. Okay, now again, you don't get this problem right here in purple very often, but I just wanted to do it to kind of build up to the next one. So if we did know the wings, so it says this area was found to the left and the right of the same symmetrical z-score. So notice that these are symmetrical, best as I could draw it, away from the origin. I point that out because there are some times that we knew an area to the left and a non-symmetrical area to the right. So this one, notice that it's phrased in such a way that it says this value is evenly distributed to the left and right of the same z-score. So this would be those wings down here. So that means if I knew the area in both, but the calculator can only find the area to the left, I just have to take that number that I was given, 8904. And this is where I was saying I wouldn't know this in the, just off the top of my head, but I can type it into the calculator as that number divided by 2. If that area is in both wings, if I cut it in half, that would be the area in the left. It's still a normal bell curve. So I do the same 0, 1. So again, when I went to my inverse norm, I actually just typed in 0.8904 divided by 2, just straight onto that screen. 8904 divided by 2. So I didn't have to refigure it on a different screen and then come back. I can type it in right there on inverse norm. You can calculate it for me, and it's going to give me the answer of negative 0.1378 if you round it correctly. Now, be careful, because the way this question is phrased, it says to the left and right of z. We have now found this one, because remember that it only ever finds to the left. That's why the answer it gave us was negative. But remember, there are 2 arrows, so the answer for this arrow over here would be the same number, but positive. So a negative 1.1378 and a positive 0.1378 would cut off an area of 89% in the middle. So the way the question is phrased when it asks for z, z being the value, basically it's asking for the absolute value of the number you get in the calculator. It's saying that because it's asking for z, not negative z. We had both a positive and a negative z answer. The calculator automatically found the negative one because the negative one was closer to the left. So the final answer we would input into XYZ would be not negative 0.13, but positive 0.1378. Okay, and that same thing is going to happen on the between problem. Now notice up here on the right, this is one arrow, this is one answer. I would never magically change this answer from positive to negative or vice versa. So this one, the answer was the answer. So the only time I have to kind of think about this are these problems where I had 2 arrows. I had to do it because the calculator found the arrow on the left, but it was just asking for the value. Okay. All right, so this is the one that's a little bit long. Remember that you can type this onto your note card, so you'll have that available to you, but if you stop and think, it does make sense. So this is the area in between here in green. So if that area is in between, then 1 minus that area would be the one in the 2 tails, just like the example we did a second ago. And then if I take that answer and then cut it in half, that would give me the area in 1 tail to the left. Now, since I did need it to do it in this order, I have to use parentheses. So when I go to my inverse norm screen, I have to use an open parentheses, do the subtraction, close the parentheses, divide by 2. So you have to type it in exactly like that. And we'll probably need to do at least one of those together, since I know it's easy to miss. So let me show you on my screen. I know it's hard to see, but just so you can kind of have that. Zoom in if you can. So I use an open parenthesis, and then I type in 1 minus. I'm using the minus over here on the side, not the little negative. 0.6826. Close the parenthesis after the subtraction, and then divided by 2. Okay, so it should look like this, where you have the subtraction. There it is. In parentheses, and then divided by 2. Okay. So when you paste, we should get a negative answer, just like the last one. So I get negative, let's see if I round this, this is still going to be 9999. Really, really close to 1, and we're going to talk about that too. Okay, so again, remember, just like the purple one, we found one of the two arrows. It found the one further to the left because of the way the calculator is programmed. So the answer I actually input into XYZ would be positive 0.9999. I do not do this on the problem that asks to the right. I only do it on the between and wings because that one has two arrows. Okay. All right, so it takes just a little bit of practice, but after you get a feel for it, and like I said, if you have these written down just to kind of look at, they're not as bad as they seem. Okay, so let's do some examples with a story. Okay, so on all those examples, we just did the comma 0, comma 1. So this time we have a little bit of a story. So now that we know all there is to know about the CDF and inverse norm, let's mix them all together and see if we can tell when we need to use which one. So this one, it says, SAT writing scores are normally distributed with this mean and standard deviations. So that's what we'll use instead of the 0, 1. They're going to award scholarships to students who are in the top 2%. Okay, so in the top 2%, that would be the area. Okay, so it's not the score, it's the area, the percent, the probability, the value. So that means we're going to try to find the score that cuts that off. So that's going to be an inverse norm problem. Okay, because I knew the area, the probability, and I wanted the score. So I'd go to my inverse norm screen. It's a top 2%, so that is to the right. So that means for my calculator that only finds left, I need to do a 1 minus. Okay, remember to do 2%, not 20%. And instead of our 0 and 1, we have a mean of 497 and a standard deviation of 109. Okay. So when you type that in, you're going to get 720. So this is not anything I need to change the sign of. 720.8586. Okay, and these story problems, they tend to have different rounding because of course on the SAT you can't make 0.85. So they would generally have the final answer as 721. Okay, but usually they're going to give you, here it is, the rounding instructions. So it says to the nearest whole number. If it doesn't have specific rounding instructions, always go 4 decimal places. Okay, next it asks us to find the 71st percentile, the 71st percentile. So all of those types of things, it's going to the left. That's kind of the most common. So that one we just get to use our regular inverse norm. Since it's already to the left, I don't have to do any tricks. And I find the 0.71. It's the same test, so it's the same 497, comma 109. Okay. So let's punch that in. Usually it'll keep the same area and standard deviation. So if you're doing multiple variations on the same problem, you just have to change the first number. And this gives me the answer of 557.3189. But again, rounded to the whole number, that would be 557. Okay. And the first quartile, percentiles, quartiles, same thing. It's still coming in from the left. So the quartile, a quarter is how much percent? That would be 25%. So the same 497, 109. And you should get 423.86. 0.4806, rounded to 423. All right, now just a few quick things. Let's kind of think if these make sense. So this one was 2%. That's really far away from the average. So notice that the answer was much farther away from the average. It was a very extreme answer. So only really high scoring students were able to earn this scholarship. As opposed to these two, 71.25, those are closer to the center than 2%. And notice how their answers were closer to the average right here. So it all fits together, it all makes sense. Also, one other thing, if you're following along with one of the newest, latest, greatest calculators, the one with the backlit screen, even fancier than this one, you may have noticed when you went to the inverse norm that you had an option there at the bottom for left, right, center. If you did, then you actually don't have to use any of my tricks. You can just choose left, right, or center. So you would just put in the number itself, no matter what, don't change it, no 1 minus, and then choose that you wanted the answer to the right. So if you felt like doing my tricks, you just wanted consistency, you would just always leave it on left and then that would work. But since you have that technology available, feel free to use it. And if you're having any trouble, I can go through that with you. Okay, so here's another one. There are some instructors that do scoring like this, where they want a certain amount of their class to get a certain score. Now, this may work to your advantage or disadvantage, because that could mean that no matter how hard you work, you wouldn't get an A if there were people in the class that were higher scoring than you. So this type of structure right here said that all of these students that made an A had to get the top 15% of the scores. No matter what they did or how hard they worked, they'd only get it if they were the top 15%. B's were 15 to 64, C's were 36 to 21. And notice how they kind of switched it. So they said top 15 and bottom 64. So you have to be careful, they switched it there. So if they asked me then to come in and find the limits for an A is the top 15%. So that would be like this guy right here in green. Okay, so that of course is an area to the right, which means I need to do the trick of 1 minus, just like that top 2% for the ACT score there. So that would be 1 minus 0.15. It's not just a standard normal bell curve. It says that the average of these scores were 73.5 and 7.9. So if I go punch that in to my inverse norm, and remember you can type it in just like that, 1 minus 0.15. 7.5 and 7.9. Then we see that actually in this class, a score of 81.6878 would receive a score of A. So in this class, that actually worked to their advantage. Okay, so basically, and does it say, yeah, round to the nearest whole number, an 82 would get this person an A. Okay. The distribution of X in this class was the 73.5, 7.9. It's basically the last two numbers we used in our inverse norm or CDF. They both use the same. So it's the mean, comma, standard deviation. A lot of times they'll ask that just to kind of get you on the right track, to remind you that it's not the 0, 1. Okay, but this, if they wanted the limits for a D, we have to be careful. This is what I was saying, is that non-symmetrical top-bottom. Okay, so we have to actually find two separate scores independently. So this, notice, is the top 79%, but this is the bottom 8%. So the top 79%, that is more than half. That's why I drew it this way. Okay, would come across the center. Okay, so we're going to point that out when we find our answer. So this is again an area to the right. So I do my inverse norm. Now I would use a 1 minus So 1 minus 0.79 with the same distribution of 73.5, comma 7.9. I'm going to punch that in. And I would get 67.1293, or rounded to the whole number of 67. Okay, now the bottom limit of a D is the bottom 8%. So that means this area here is 8%. And now that we're looking at it from the bottom, this is now to the left. So that would be an inverse norm. And I would just input the 8. I don't have to do the 1 minus. We're not coming from the top. It's an automatic left. Same 73.5 and 7.9. And when we punch that in, make sure to do 0.08, not 80%. You should get 62. Let's see, that'd be 3,999, which would round to the whole number 62. Okay, so in this class, earning a D would land between the scores 62 and 67. Okay, so in a normal class, a 61 would have still been a D, but in this class, the way that this percents lined out, that actually gave them the F. That would have put them in the bottom 8%. So I mostly point that out because sometimes students, after seeing that, they're like, oh, why don't we do that? That's basically what the curve is. You know, when you hear about grading on a curve, it's basing it based on the percent in the class rather than your hard work and your independent scores. So that's why it doesn't seem fair for especially people like the 61 that worked hard and just had peers that were a little different than them. All right, so in these last examples here, like I was saying, it's all mixed together. So we have to think about, do we need the normal CDF or do we need the inverse norm? So we have this birth weight example here. Here's our mean and standard deviation. That's what we'll be using in our inverse norm and or CDF. So this one, we wanted just the Z-score. So remember back in the day when we learned about Z-score, that was back from chapter 1. Remember, we learned it right there at the end. We just took the value of interest minus the mean divided by standard deviation. But you did have to be careful to do the subtraction first. So we need either parentheses or we need to hit enter twice. So back over to our example, Z-score for the value of interest, 3704. Minus the mean of 3432 divided by the standard deviation of 482. So you have to be careful typing this in. I recommend typing 3704 minus 3432 and then hit enter. So we get the answer 272 and then do the divided by 482. So just do it in 2 steps like that. So I got the 272 from the subtraction, and then I hit divided by. So I didn't have to retype 272, I just hit divided by, and it finished it up. And that gave me 0.5643. So what did this mean back in context? That means that on the normal bell curve, 3704 was above this, the mean right here. In this case, it wasn't just 0. Remember, the mean was the 3432. So looking at our number, 3704 is indeed higher than 3402, but 0.5 is pretty small. And you can see that this isn't a whole lot higher. So it wasn't a very extreme birth weight, but it was higher than average. Okay. Okay, and then it says, what fraction of infants would you expect to have a birth weight above 4140? So is this a probability? Is this an area? Or is this an actual score? So this is the birth weight. So this time they're giving us the number down here, 4140. Try to think about where that number would go. Would it go inside the curve? Would it go down here to indicate along the axis? So again, kind of thinking in context, we can see that this is above average. So I'm going to expect an answer that reflects that. Okay, so I have the birth weight 4140. Since it is a score, I'm going to go back to the last lesson and use my normal CDF. Okay, remember that that one was lower bound, upper bound. So this was a basically infinity. My trick was to use that -9 to the 9th. So that is my lower bound. My upper bound was that 4140. It's a mean of 3432. And the standard deviation of 482. Okay. It is still in the second vars. It's the second option. Remember that when you're doing the -9 to the 9th, you use the little negative on the bottom, not the minus on the side. 4140. Don't forget to change your 0 and 1 to the context of this story, 482. And you should get an answer of 0.9291. Okay. Or as a percent, that would be about 92.9%. Okay. So the fraction of infants is 0.92%. All right. So that was a test. We actually did that one wrong because of the way it's worded. So it says, what fraction of infants would you expect to have birth weights above this? So thinking back in context, I was thinking 92%, that's pretty high. And this is a really high birth weight, right? So that's too high. We found this number over here. This was the 93%, basically. But it wanted to know the rare babies, these ones that are above. So this one I would actually need to do a normal CDF. Okay, above, so going from 4140 up to positive infinity, 9 to the 9th. And you're going to find something very similar to our last answer, very related. So if we go change that real quick, in our normal CDF, the 4140 being the lower value, 9 to the 9th being the upper, same mean, same standard deviation. Instead of the 93%, we get the other 7%. We get 0.0709. Okay, so this blue one would be below, the fraction of babies below. Okay, and this one would actually answer the question they asked us and find the fraction of infants above. Okay, so I just kind of stop and think about your answer. So we all make mistakes and it's easy to misread something. So if you just say, okay, I kind of expected this answer, that can help you catch a mistake. All right, so next it says that with these babies, they wanted to find the lowest 5% of the babies so they could kind of make sure they're doing okay. So this is the percent. This would be the number inside of the curve here, 5%. Okay, so since it's the inside number, not the score down here, that was the inverse norm. Okay, 5% on the left side, the low 5% would just be a left tail. So I just typed that number straight in. We still have the same context, 3432 and 482. So punch that into your inverse norm. Four 32 and 482. Okay, and we get a birth weight of 2639.18. Okay, again, thinking about our answer in context, this does make sense. The average was 34. This is below average. It is far below average because this is the lowest 5%, so that's pretty rare, right? So we expect a number pretty far away from the 34, 32. If I got something like a decimal, I'd be suspicious. I shouldn't be getting babies that weigh 0.7 pounds or grams, right? That would be terrible. So this answer makes sense. It's lower than 34, but still fits in the context of the story. So just always kind of double check yourself with the context when possible. All right, now this last one about the giraffe. Kind of stretch our minds here. So it says normally, what is the median? And they're thinking, oh, what's the formula? Well, if you look back, you learned about this. And here, on slide 17. So when we talked about the skew, the left skew, the right skew, we talked about how it pulled the mean away from the median. And if it was right skewed, the mean got pulled up more than the median. But all of these things we're talking about now are normal bell curve. That means that things are symmetric. And when it was symmetric, those all lined up. The median and the mean and the mode should all be the same. So in this case, when they asked us for the median, it should be the same as the mean. So the answer would just be 17B. That is because that was the mean. So we knew that because it was symmetrical, because it's a normal distribution. Okay, so the distribution would be the mean of 17 and the standard deviation of 0.9. Okay, that means that's what we would use in all of our inverse norms and CDFs instead of the 0, 1. What is the probability that we randomly grab a giraffe from the zoo? And it is shorter than 17.8. So let's think about it real quick. Expect our answer. Shorter than 17. So looking at our bell curve, the average was 17, right? So the middle is 17. So shorter than 17.8, that should be more than half of the giraffes. Okay, so let's see what we got. So 17.8, that's a number down here, a score. Okay, so that means we're going to be doing the normal CDF. Okay, so that is going down to infinity. So -9 to the 9th. It is shorter. I'm not making another mistake this time. Up to the 17.8 that we were interested in, not comma 0, comma 1, comma 17, comma 0.9. Okay, just like this. So if we punch that into our calculator, let's check out our giraffes. And we find, just as we expected, higher than 50%. We had 81.29, or basically 81.3%. So if we rounded this, it would be 81, and that 296 would round up to 30. Okay, and last, the 85th percentile. So remember, percentiles, quartiles, all those things, those are just standard from the left. So those were the easiest ones. So 85%. Go inside, and it's looking for the score right here. Okay, this is higher than average, so I expect my number to be higher than 17. Since it was an inside number, that's an inverse norm. Inside, inverse. To the left was the easiest one, so I just do the 0.85. And then comma 17, comma 0.9. Let's check it out. 85, 17.9. Watch all your decimals. And you should get, just as we expected, 17.9328. Even compare it to our last answer. So this one was 17.8 was 81%. 85%, a little bit higher, was 17.9, a little higher. It all goes together. So in a problem like this, especially if you had it on a test, you could kind of compare and contrast and make sure your answers fit together. Okay, all of these things even line up, I wanted to point out real quick, with what we learned before. So on this answer, remember when we got 0.999, this might have looked familiar if you thought about it back from chapter 1, down here, when we talked about these guys right here. Here's that 68% was 1 standard deviation away from the mean. So right here, when they gave us 68% in the middle, we found that it was 1 standard deviation away. So that's how they found these numbers. These were all just estimates to kind of get used to the idea without having to do all the calculations just yet. So it all fits together. It's the same thing. That's what that empirical bell curve rule was talking about. Okay. This last slide is just a bunch of problems with their answers. So if you just kind of wanted to check yourself, especially if the XYZ was being funny, you could kind of go through, make sure you were using the right inverse norm versus CDF. You could ask me questions about any of these. So this is just some extra kind of examples and practice for you. So as always, let me know anything that gives you trouble and we can go through it together.